So this our first session on OpenMP programming, and let's get started. So for today's course, I'm planning to cover the motivation behind using OpenMP, or motivation behind having the multi-core systems, and why do we need shared memory programming API like OpenMP for multi-core systems. Then we will look into the classifications of the parallel computers and what are the different types of parallel computers that we have. And I will look into the few of the nuances behind that. And towards the end, we will see how to write a parallel program, how we can go with writing a parallel program. So not exactly writing a parallel program, but the high level overview of how we can write the parallel program. So we will not start with writing the hello world program today, but we'll see the high level details for it today. So let us begin. So let me move to the next slide. So first of all, there is this what is OpenMP is like. We should be clear about it. So OpenMP is like shared memory parallel programming API for a shared memory system or the multi-core system. But before, so this is the formal definition, but we should be knowing a bit of history, like why do we need the multi-core systems at first place, and why did it came in first place? So let us look into a bit of why it is there. So if you can see this on screen, so I hope that you are able to see the title. I'm not sure if this. Sorry, are you able to see the screen?
Yes, yes.
Yeah, so this is the uh, graph in which we can see that x-axis has the millions instruction per second and y-axis has the years. So so this graph shows that from 1975 to up to 2000, there is a significant improvement in the number of instructions that were executed per second by a particular core. And the reason behind this is that there were two things. First is actually three things. First is the clock cycle improvement. And apart from that, there were also architectural improvements that were happening at the chip level. I mean, at the computer architecture level. And second was this clock cycle improvement. Apart from that, there were also more and more transistors that were getting placed inside the hardware chip. And all these things were leading to the automatic performance improvement, because this performance improvement was coming from the hardware level itself. So as a software developer, you won't need to write some efficient program. You just can wait for, let's say, a few years, and your program will automatically start running faster because the hardware is improved. So so in summary, single processor performance experienced dramatic improvement from clock and architectural improvements. So from our architecture point of view, there were pipelining and ILP, instruction level parallelism, that were there, which were causing this improvement. And obviously there was clock frequency that was getting improved. And as we know that there is this Moore's law, where it's an empirical law which says that number of transistors that we place on our IC or integrated circuit doubles every year. So we were also observing the performance improvement from this. So due to all this, we were experiencing the automatic performance improvement. So so this is one thing. But after early 2000s, if you can see, the clock frequency was increasing quite comfortably. But during the early 2000s, and if you can see, the clock frequency started tapering. If this is not the complete graph, but here, if you can see, till here it was increasing, but after this it would hit a plateau because of a problem that is known as a power wall problem. So what was happening was, since we are going on increasing the number of sorry, we are increasing the clock frequency. What will happen is that heat dissipated by the transistors will go on increasing, and due to that, uh, what will happen is that our system will get it is will dissipated more and more heat. And this chart shows the amount of heat dissipated on y-axis and the processor technology on the x-axis. So as you can see here that the heat dissipated is increasing from I386, from I486, and so on till Pentium. And this is the extrapolation of this chart. So it shows that if we keep on increasing the clock frequency further, it would sometime reach to the amount of heat dissipated from the nuclear reactor. And if we keep on going further, it will reach the point where it dissipates the amount of heat which is released from the rocket nozzle, and so on till the sun surface, heat on the sun surface. So yeah, so this is the power wall problem. So the crux is that we are going I mean, we are just increasing the clock frequency, and due to that, the amount of heat dissipated is more and more, and because of this we are having this issue that we are hitting the power wall problem. So we can't increase the clock frequency beyond certain level. So I hope this is clear. Any questions up till now? Wait here for some time. Okay, no questions.
Hello.
Yeah, please go ahead.
Hello. Yeah,
Yeah, yeah,
I
please go
just
ahead.
wanted to know that as you are saying that the processing speed and the complexity, like the speed and efficiency has increased drastically, and they are limited because of the thermal dissipation.
Hmm.
I wanted to know, has the Moore's law come to saturation, or we are moving to?
So Moore's law, as of early 2000s, the era which we are looking here in, right? So the number of transistors that were placed on IC were still increasing. So we'll see that in the upcoming slides. So the number of transistors that we can place in that uh, IC or integrated circuits were increasing, but the clock frequency we were not able to increase that beyond the particular limit during this era. So I'm talking about this era, 2000s, early 2000s. So if you're talking now,
Okay,
then
I mean,
yeah, I think, sorry, go ahead.
yeah, yes, yes. Like I think nowadays we hear a lot of quantum computing is
Yeah.
booming.
So
So what like so HPC is in what place and how it is efficiently managing these things, and what is like why like you are saying that we can put more transistor on a chip. So like HPC is in what zone we are going to use it?
okay, so first thing that I want to clarify. So I was talking about this early 2000s era, but yeah, that point is correct. Like if you talk about now, 2020, after 2020, then Moore's law is like somewhat now getting. So what I'm trying to say is that Moore's law is now getting uh, dying in some sense. So the thing is, we are now not able to place like we are not able to double the number of number of transistors that were placed like it was there in this era, right? So it's not doubling now every year, but still we are able to place more and more number of transistors. So you can see that there is this thing, right? That uh, 3 nanometer technology is coming, 5 nanometer technology is already there. So in that sense, we are still in progress, but yeah. And so HPC will be still in place, I'll say, but in coming years, quantum computing will also play a significant role in the computing industry. But yeah, still HPC will still be there. So quantum computer, the amount of or the type of work it can do is still in quite research. So I can't comment on that. But yeah, according to me, HPC will still be there and it will still be in use. Did I answer your question? Or
Thank
still?
you. Yeah. Thank
So I'm assuming that they are clear up till this point that what is power problem. And yeah, so let us move ahead unless we have any questions. Yeah, so as I said, right, the clock frequency after this point, 2000, early 2000, started tapering or it hit a plateau, if you can see here. So these are the clock frequency of Intel and AMD CPUs. So after a particular point, you can see that there is this flat line that is coming. So it is getting flat. So basically the issue is same, right? That there is this heating problem and we can't just increase the clock frequency beyond a particular point. And due to this, even Intel has to cancel some of its processor because of the extreme power consumption and heating problems. So yeah, this is the thing. So we hit the powerful. But now what is the solution to this? So if you can see, as I said, right, during this era, early 2000s, the number of transistors that we can place in the IC were still increasing. So you can see this straight good line, right? But as we talk, the clock speed is now hitting a plateau. We can't increase the clock speed beyond a particular limit. Similarly, the power consumption at the core was also increasing. So we can't just go and keep on. It will also hit a plateau. After that, we can't just keep. It will consume the power beyond permissible limits. Similarly, for ILP, the amount of parallelism that we can extract out of our code was also hitting a plateau. We weren't able to extract more ILP out of our code. So yeah, but this thing was steadily increasing, right? During this era, I'm talking about this period where these problems were there. So during this era, this number of transistors that we can place were still increasing. So what people thought was why to use a single core? Let us use multiple cores, and this led to the evolution of multi-core CPUs as well as GPUs. So this is how we came to the today's era of multi-core systems. So even your smartphones today will now have multiple cores. Similarly, your laptops will have dual core, quad core, and so on. Multiple cores they'll have. So this is what it is. So this is how the multi-core systems came into picture. And now this will this will be more clear. So this OpenMP is a parallel programming API for writing. For using this multiple for this shared memory system or the multi-core system. So basically, what we can do with OpenMP is that we can use this multiple cores to write the parallel programs. So since we have multiple cores, we need to make sure that we use all of these cores, and for using that we have this API called OpenMP. So the point here to note is that since the parallelism is exposed to the software now, it's our responsibility to make sure that we write our programs in such a way that this we make best use of this parallelism. Yeah, so that is it. Any questions on this slide? Or
Am I audible?
yeah.
Could you please explain what internal or hidden parallelism is, like in short?
Okay, ILP, instruction level parallelism.
Yes.
So ILP is like, let's say you have a code. There are multiple instructions in your code. Let's say I1, I2, I3. Let me use my whiteboard so that I can explain it better to you. Just give me a minute. Yeah, just give them a little. Yeah. I'm looking if there is any option to share another screen.
No worries, like even a small verbal explanation will do, and I can look it up.
Okay, let me share this. Can you see this whiteboard now?
Yes, yes.
Yeah, so let me explain it in this way. So there is this program P1 you have, right? In this program, you will have set of instructions I1, I2, I3, right? Let me put more also. And then you have the CPU and yeah. So let's say the instruction I2 is an IO instruction. So what will happen is that instruction I1 is executing on CPU. You can, okay, so wait. Yeah, so there are a set of instruction with the CPU, right? It can execute. Now, let's say a particular instruction is an IO instruction. Then what will happen is that it will go for an IO. And meanwhile, CPU can pick up some another instruction for its execution. So this is the kind of the multi-processing kind of thing. So
Right.
that is what we mean by instruction level parallelism. So while one instruction is going for IO or something like that, you can pick up some another instruction. CPU can pick up some another instruction and can execute that. So the thing is that CPU will not leave idle at any point. It will have the multiple instruction that it can execute. And the thing is that let's say instruction I1. So exactly the parallelism comes from let's say instruction I1 and I3 are independent, right? So instruction I1 and I3 can be executed in any order. So that is exactly what is the instruction level parallelism. So let's say I1 was the add operation on A and B, which are some variable. And instruction I3 was multiply operation on some different variables C and D. So these two instructions are in no way dependent on each other, right? Because they are manipulating different variables. So they can be executed in any order and independently. So that is what is the instruction level parallelism. And CPU can execute these two instructions, I1 and I3 in any order, right? I hope I was clear, or did I
Yes.
missed?
Yes, that gives a like good visualization and understanding of the concept. Thank you.
Yeah,
Yes, how does the CPU determine if these two instructions can be done in parallel? I mean, like, are there any flags or something written in the program itself which can help in that?
I think there are some architectural way in which we can determine that. Frankly speaking, I'm not sure how that is done, because that is completely based on the architecture. And also compiler is involved here. Compiler is in some way able to determine whether these two instructions are somewhat correlated or not during compilation of the program So I'm not 100% clear about that part, but yeah, this is what at high level ILP is.
So ILP is not possible if there's an instruction followed by an IO instruction which is dependent on that, right? So if there's a
Yeah, so
yes, sir.
let's say yeah, so if there is if we are adding A and B and are putting in some variable, let's say C, so A and B are being added and placed in C. And there is this next instruction multiplication, which is using the C to place in some variable, let's say X. Then this is not possible, right? So then we can't parallelize these two instructions. So this is what it is. And I think at architecture level and at compilation also, we can determine that how much instruction level parallelism we can extract from our code. So the point that I was trying to highlight here, I hope you can see the slides now, is that the instruction level parallelism will also come to an particular saturation limit after some time. So there is this limit, or there is this upper cap on how much parallelism, I mean, instruction level parallelism that you can extract out of your program. I hope that this is clear.
Yes, that makes sense. Thank you.
Yes, it's clear.
Yeah, please go ahead. I think someone was speaking, right?
Yeah, actually the slides that you are showing are not visible. The whiteboard that you are displaying it's right now.
Okay, I think I need to share again. Okay, I think now it should be visible.
Yes.
Yes.
Yes, it is.
Yeah, okay, then I'll go to next slide if there are no questions. So I hope this gives you overall a good picture about why we need multi-core systems and why something like OpenMP exists and is thriving. So basically OpenMP is like a standard for writing the shared memory parallel programs, and it's used as the benchmark. So that's kind of motivation for us to why we should study the OpenMP. So this is the chart which shows the high performance computing milestone. So there is, so you can see that the x-axis shows the years and y-axis shows the amount of computation that we can achieve. So if you can see, there is this kiloflop, megaflop, gigaflop, and so on, exaflop. So can anyone tell me what is flop, or if anyone knows that what the flop is, then can they type in the chat?
This floating point operation.
Yeah, so basically during 1960s we were able to achieve some kiloflops of floating point operations per second using the supercomputers that we had during that era. And if you see, this is quite an old chart actually, but if you see in today 2023, we have actually reached this exaflop stage. So the current fastest supercomputer that we have, which is Frontier, has like it is able to achieve this 1.5 exaflop of floating point operations per second. It was able to it is able to perform. So this is the chart, right? And you can see from this onwards, this period onwards, there was this GPU powered supercomputers also that were coming into picture. But yeah, for this course, we'll be studying the shared memory system and OpenMP. And yeah, but yeah, one thing to observe in this chart is that one interesting thing to observe here is that during 1980s, if you see, we were able to achieve 1 gigaflop of computation, right? Per 1 gigaflop per second. And today we are at the exaflop stage. And one thing here to notice is that during this period, the clock frequency, how much it has increased. Like during 1980s, it was like 100 megahertz of clock frequency. But can anyone tell me what is the clock frequency of our CPU that we have nowadays? For GPUs, it will be even lower, but CPU, what is the clock frequency? If anyone knows, generic clock frequency.
Usually 2.4 gigahertz. Usually 2.4.
Yeah. So
Somewhere
yeah,
around
any other?
5.9.
Yeah.
Intel's
Any
like the latest generation have 5 to 5.9 gigahertz.
Okay. Anyone else who want to speak up? Like what is the clock frequency that we have nowadays for any CPU, normal CPU. Okay, if no one wants to speak up further, then okay, that's fine. So what point I was trying to drive here was that let me share my whiteboard again. Yeah, so the point that I want to drive here is that from 1980s to 2020s, the computation power is increased from 1 into 10 to the power 9, which is gigaflops, to exaflop stage, right? But the clock frequency of a particular core, I'm talking about a particular core, has gone only from megahertz to, let's say, let us pick up the maximum 5 gigahertz, right? So this increase, if you see from here to here, it's just 50 times, right? If I'm not wrong, this is 50 times. But if you see this one, this is like whopping 10 to the power 9 times, right? So where this not 10 to the power 9 times, but it's 10 to the power 9 of improvement. So the point that I'm trying to highlight here is that this performance improvement of 10 to the power 9 is not just because of the clock frequency increase, because clock frequency hasn't increased much. It's of, I mean, what I'm trying to say that it's of order of 10 here, while this is of order of 10 to the power 9, right? I hope this is visible. Yeah, this is of order of 10 to the power 9. So the point that I'm trying to derive here is that the clock frequency started, I mean, it has not increased much in that magnitude, but the improvement is significant, right? 10 to the power 9 of improvement. So this is coming from this multi-core setup. So this supercomputers that you are seeing on the screen, let me go back to the slides. So the supercomputers that you are seeing, the names that you are seeing, right? Here are all multi-core systems, as well as actually they are heterogeneous systems. We'll see what is heterogeneous system in next couple of slides. But yeah, they are using multi-core setup along with other things. We'll see. So this also serves as the motivation, right? That most of these supercomputers are multi-core, and we should know how to program these multi-core systems. So I hope this point was clear, or if anything is missing, then please unmute and ask the questions.
Excuse me, I have a doubt.
Yeah.
So, OpenMP may not work in GPU environment.
I'm not sure if we can run OpenMP on GPU. Personally, I haven't done that. But on multi-core systems on your CPU, you can run OpenMP on your shared memory system, which is on your laptop or any shared memory system. We'll see what is shared memory system also. Till now, we haven't covered that. I think in next slide, we'll cover that. But
This,
yeah, I think I haven't tried running it on GPU, running OpenMP on GPU.
What my question exactly is that the shared memory programming, do we have any like OpenMPA? Is there any framework for GPU?
Yeah, so we have this CUDA as well as OpenACC, which are for GPU programming. So if you see this OpenACC is more like, so there are two things. Let me share. So OpenACC is more like OpenMP, in which you will have constructs like OpenMP to parallelize your code on GPU. And then there is this another slightly lower level language than OpenACC, which is CUDA, using which you can write, you can write programs which can be run on the GPU.
Then CUDA is shared memory it uses shared memory architecture.
Okay, coming to CUDA, so there is this GPU, right? GPU itself will have its own memory. So you can in some way say that, so GPU also has cores. So internally it is kind of a shared memory system.
Okay, it's
But,
already a shared memory system. Okay.
Yeah, but you'll see in later slides that it is called many core system rather than multi-core. But yeah, internally it is kind of a shared memory system, I would say, because there is this RAM that GPU has. It has its own RAM. It has its own core. And
Yes.
if you see, I'll show you the shared memory architecture also in very brief. So it is kind of shared memory, but yeah, it is considered as many core system.
Yeah, understood. Thank you.
Will OpenCL also be used for this heterogeneous kind of parallelization?
Are you talking about OpenCL or OpenMP?
OpenCL.
Okay, I'm not very much sure about OpenCL, whether it's used for heterogeneous programming or not. I have not used OpenCL very much, so I'm not aware about it.
Thank you.
Sir, can you tell about the performance differences of parallelizing a program on a framework like OpenMP, which focuses on CPU, versus parallelizing the same program on something like CUDA, which would deploy that workload on a GPU? Like, what are the performance differences, and why would we choose one over the other?
Okay, so let me briefly explain this also. So, let us take these two scenarios: CPU parallelization versus GPU parallelization. So let us say that you have an application which is having a lot of number crunching operation. So let us say that you have this application like vector processing, or let's say image processing. So in this kind of application, if you see, let us pick up the image processing example. You have to, sorry, you have to do same operation on set of pixels, right? You have this screen, and you have to perform same set of operation on particular pixels of the screen. So here you have a lot of data, and you have to perform same operation on that data. If that's the case, if you have a lot of number crunching operations, then this GPU parallelization will benefit, because the reason is that it is a many core system. And if you see, the number of cores that GPU will have is around of order of 4,000 something, right? Around 4,000 cores it will have. And the thing is, and in the CPU, there will be some tens of cores, order of tens of cores will be there. So if you have the number crunching operation, then GPU is better. Else, if you have heavy computation kind of operations, so the difference between this CPU, each core of CPU and each core of GPU, is that the number of cores in CPU will be less, but each core will be powerful. It will have a clock frequency of 2 gigahertz or something like that. Will CPUs, for CPU, it will be the 2 gigahertz of frequency. Means that each core is powerful, but for GPU, each core will not have that much frequency. I think it's of order of 100 megahertz. So each core is less powerful than CPU's core for GPU. But if there is this nice parallelization that you can extract out of your code, and if you have to perform same type of operation on large amount of data, and if you can parallelize it very efficiently, then you should go with GPU. Else you have to go, I think you should go with CPU and use some framework like OpenMP. I hope that answers your question.
So, sir, if so for example, if we have some sort of a data set, and each each data item in the suppose an array needs to go through a different sort of computation. So, is that possible through CPU parallelization as well, or do we again follow the vector model in there?
I think, see, the case here is that if you want to do any computation, you can do it on both CPU as well as GPU. Let's say you have some computation which is not even parallel, you can even do it on GPU. That's not an issue. But what we are concerned about here is that performance. So let's say you have 4-core CPU, and let's say you want to execute a program P1, which is not at all parallel. Then you can execute on GPU core as well as CPU core. But it's better to execute on CPU core because CPU core will finish it much quicker than GPU core. And yeah, I hope that answers. Like, you can do it either ways, like either on CPU or GPU. The only thing is the performance. Any operation you can do on GPU nowadays.
Okay, sir, got it. Thank you.
Okay. Any other
I had
questions?
a small doubt. You said that the speed of GPU is less than CPU. So if I am like writing a single instruction, that means CPU will process it faster. But if I want to do multiple instructions, and because GPU has multiple cores, because of parallelization, we will be executing all the instructions parallelly and getting the output quick, even though the clock
Yes.
speed is less.
Yes. So
But in
okay, let
CPU, it
me.
will be sequenced one after another. That's why the waiting
Yeah.
time will be more.
Yeah. So okay, I'll quickly summarize what I was trying to say here. Let's say you have a vector. Okay, let's say you have this problem statement, right? There is this vector of size 10,000, right? That you want to perform some operation. Let's say you want to add 2 to each element of this vector of size 10,000, right? Now, let us say you have CPU and GPU. So on CPU, let's say you have just 4 cores, and on GPU you have, let us say 2000 cores. So in GPU, this can be done very quickly, right? Because if you want to just add 2 to each and every element in this vector, there are 2000 cores, and each core can pick up, let's say, 5 cells in this vector, and they can finish it quite quickly. Even their frequency is less, right? Even they can perform this task slower. While in this case, each core has to, in CPU's case, each core has to take up around 2500 cores, 2500 cells, and need to perform the operation. So if there is this nicely parallel operation coming into picture, then I think GPU is better than CPU. But yeah, there are cases where CPU is better. Let's say there is this very expensive operation. Let's say this is a very expensive operation. It's not just this simple operation. Then CPU parallelization might be better than GPU, going with GPU. We'll see there are also other scenarios like communication between core and other synchronization scenarios. So yeah, so this is the crux of it. I hope you are getting.
Yes, sir. Yes, sir. Got it.
Okay,
So
let
CPU
me.
would be better for multiple instruction, multiple data kind of a programming model, right?
Yeah, in some sense, if multiple instruction, but yeah, you need to see how much parallelism it is there in that. I'm not sure if, I mean, what scenario you're talking about. Multiple instruction, multiple data. Yeah, that is correct. But in GPU also you can have multiple instruction and multiple data kind of scenario. And if there is more parallelism in that case, I mean, based on scenario what you're talking, then GPU might be better. The thing that it boils down is that it should have, depending upon the amount of parallelism that you can get out of that code. If it's a highly parallel code, then I think GPU is better. Else, you should go with CPU parallelization.
Okay, sir. Thank you.
We will come to this multiple instruction, multiple data framework. Yeah, but let us move to slides for now. Okay, so let us look into the kind of parallel platforms, and the classification of the parallel computers also will look next. So first 2 categories are shared memory system and distributed system. So let me quickly draw this. So in a shared memory system, we have this CPU cores, multiple CPU cores, or let's say this is not CPU, but it's a core. Some tens of cores we have. They are connected via some interconnect bus. And we have this common memory, which is RAM. And each core will have its own cache, like L1, L2 cache it will have. But yeah, by and large, the largest memory that it needs to access is the RAM, which is shared. And hence it is known as a shared memory system. And using OpenMP, we'll be doing parallel processing on this shared memory system. So OpenMP is the API for parallel programming on the shared memory system. So your laptop, the CPU within your laptop will be having multiple cores, and how to parallelize your application. Let's say you have app 1, how to parallelize it on this multiple cores. You will see using this, how to do this using OpenMP. Next one is this distributed setup. So difference here is that this is in this case, okay, let me go to the next one, core 1, core 2, and so on, core n. Each will have its own memory, memory 1, memory 2, and so on. And so this is kind of a single system itself, right? It has its own core and memory. But the thing is, this set of systems can communicate with each other via interconnect or some bus. They are connected via some bus. And so let's say each system will do its own computation and will store result in its memory. But after doing some computation, they might want to share the result, and they might do it via send and receive signals. And there is this popular framework which is known as MPI, which is used for programming the shared memory systems. So if you are interested, you can check out this one also. Okay, now let us move to let us move to next with the slides. Yeah, apart from that, we have this GPUs. So GPUs are, as I said, they are many core systems, and the difference between shared memory system and GPUs is that they have large number of cores compared to the shared memory system. So shared memory system or multiple system might have few tens of cores, while GPU will have thousands of cores. And in some sense, GPU is also a kind of shared memory system only, as I explained. Like it will have its own RAM, and it will have its own, some registers as well as a few other things also. But yeah, by and large, it's in a different category with just GPU. And GPU and CPU are together kind of a distributed system. I'll show you why I telling that. So let me go and switch to this. So in case of GPUs, we have this GPU, which itself is like a shared memory system because it has its memory and cores. But why am I saying like it's like a distributed system also? Because it needs to communicate with CPU via send and receive signals to get data and to get the data and to send the data back. So yeah, it's a combination of distributed plus shared memory system. So this is CPU. I hope this is clear. Now let us move back. Yeah. So apart from that, we have FPGAs, which is field programming gate arrays, which are configurable after manufacturing. And then we have ASICs, which is application specific integrated circuit. So if you want to have a system for a particular domain, like let's say you want to have a specific IC for just graph processing or just image processing and so on, then you can use ASICs. And yeah, and if you put all this together, then we'll have a heterogeneous system. So heterogeneous system is like a distributed system, but each node in that distributed system might be a shared memory system, which is multi-core system, or a GPU, or a FPGA, or ASIC, and so on. It can be something else also based on your requirement. So most of the clusters that you saw right in the previous slide, not clusters, but the supercomputers are actually the heterogeneous system. So they are not just multi-core, but they have many things. They are distributed clusters with multi-core CPUs, GPUs, and so on inside them. Any questions up till now? Okay.
Sir, on performance basis, can you just give a snippet of how these five, not the other than heterogeneous system, these five types of system, on what parameters we'll choose each one of them? Like on what favorable conditions we'll choose if a problem is there, if what type of problem we'll use these systems, like these five systems.
Yeah, so that will depend upon your application as such. So this last one, ASIC is very specific to the application. So if you, let's say, if you have an ASIC for a particular scenario, then yeah, you should definitely execute your code on ASICs, but they are very application specific. So there might be some application for which you might not have ASIC. Apart from that, I've already explained when to choose multi-core versus many-core, that is shared memory versus GPU.
Yes, sir.
Distributed system, I like, it's just a cluster. So in distributed system also you can do you can choose in case of high workload, but it depends upon I mean, that is very specific to the thing. Like most of the clusters are distributed systems. So in generic case, you can also pick up the distributed system. But yeah, if your question is like in which scenario, what you will pick up, the shared memory versus GPU is kind of clear, but the FPGA is very useful in the case where you have the scenario where you can't I mean, after manufacturing, you want to modify the or you want to configure the your IC, then yeah, you can use the FPGA. But yeah, I think I'm lacking the clarity here. But if you have any questions, then you can ask me now.
Like if the application changes continuously, then we can use FPGAs. Are you saying that?
No. I think so. FPGA are configurable after manufacturing. So for particular scenario, let's say you want to place some IC inside a nuclear reactor, then you can't just go inside a nuclear reactor and fix your IC, right? Let's say if something happens. So in that case, you might need something like FPGA, which can be configurable after manufacturing.
Okay.
I hope this is clear.
Yes, sir.
So the question here is like, what is best suited for which scenario? So this is kind of a quite difficult question to answer because there might be multiple scenarios. But in general, as I said, as a rule of thumb, you can go with computation. I mean, if there is this, I told you, right? You can choose between CPU and GPU based on your type of parallelization that you can extract. And distributed system you can use in combination with I mean, this shared memory system and GPU to get a better performance. As a cluster, you can do much better cluster of this multi-core as well as many-core systems. I hope I made it clear, or did I make it more
Yes.
confusing?
Yes. Yeah, I got the ideas.
Okay, let us move to next slide, which is about classification of the parallel computers. So in this case, this is also known as Flynn's taxonomy, which is in which we classify the systems based on the multiplicity of hardware, especially with the multiplicity of the instruction stream and data stream. So let us look into the whiteboard now. Okay, so based on Flynn's taxonomy, this parallel systems are divided into 4 parts based on instruction stream and data streams multiplicity. So if you have single instruction stream and single data stream, then it forms SISD kind of architecture, which is single instruction, single data. So in this case, it has a single instruction as well as single data stream. So this is kind of a uniprocessor, right? That you are just processing one instruction and then to one set of data. Similarly, if there is single instruction and multiple data, then it forms multiple instructions and single data, then it is MISD, multiple instruction stream and single data. Similarly, multiple data single instruction is SIMD, which is single instruction multiple data, and this is MIMD, multiple instruction multiple data. So okay, so this SISD is like a uniprocessor, right? You are just executing one thing at a time. You are doing one thing at a time, and this is kind of absolute nowadays, because nowadays even your phone or smartphone or anything will come with multiple cores, and you won't be having this kind of architecture, or you won't be practically using this architecture nowadays. Next is MISD. So this one is also, just a minute, something is wrong. Yeah, I think this, okay. So for MISD, also there are very few practical applications that are built on this MISD framework. That is, you have multiple instructions that are working on single set of data. So this MISD also has a very few practical application, and because of lack of the practical application, there are very few systems, very few MISD system. But coming to this too, SIMD and MIMD, we have many practical applications. So this SIMD system is kind of a vector processor, because you have a single instruction and you are performing it on multiple set of data. So vector processing is one of the example of SIMD, because let's say in case of vectors, if you want to perform, you have a vector, right? So you want to perform same instruction, let's say adding something to all the elements on the entire, all the cells in the vector, then you have just single instruction that you want to perform on multiple sets of data. So vector processors are the example of SIMD system. And coming to MIMD are multi-core CPUs or multi-core systems that we talked, right? Multi-core are the examples of example of MIMD, because you have multiple instructions, and that too you can there are multiple instructions that you can execute on multiple set of data. So if I can show you this properly, let me see if I can use my whiteboard again. Okay, so what I mean to say by MIMD is that let's say you have core 1 and core n, and you have some operations, random operations, right? Let's say multiplication, division, anything. Then, and that to one multiple sets of data, then core 1 can perform one particular instruction or multiple instruction on some set of data, as well as core n can perform some different set of instruction on other set of data. So it is multiple instruction, multiple data kind of an architecture. So I hope this was clear. Let me move back to the slides. Okay, so here it is the same thing that I talked, right? SIMD and MISD and MIMD. And yeah, heterogeneous system, shared memory system, distributed systems are all the examples of MIMD. Similarly, vector processors, and in some sense, GPU are example of SIMD. GPU, you can't tell it's completely SIMD, but yeah, vector processors are the particular example of SIMD. Okay, any questions up till now, or we can go to next slide.
I have one. So,
Yeah.
with respect to MIMD, where the cores are independent, like, is that the rationale behind MIMD being an MIMD and not SIMD? Like in SIMD, I believe like cores are dependent on each other because of shared memory. Is that the reason?
No, I think we are confusing here multi-core with SIMD, but they are quite, I mean, what I'm trying to say is that here it is single instruction that we want to perform multiple set of data. If that is the kind of scenario that you are having, then it is SIMD. And if your architecture is designed specifically for that scenario, like vector processor, then it's an SIMD kind of architecture. I hope that is clear.
Okay, so it's based just on the architecture and not the mutual exclusivity of the cores.
Yeah, kind of, because it doesn't, this classification doesn't take core into account. It just takes this instruction stream and data stream into account.
Okay.
Okay, let us move to next slide. Yeah, so now let us look into writing the parallel programs. We'll look at high level overview of it. We'll not start writing the program from today. But let us say that you want to write a parallel program. So let's say you have a 10 core CPU. What naturally you want to do is that you want to divide your, you want to find the parallelism in your code, right? And want to make use of that 10 cores to divide the task among that 10 cores. So that is what is the partitioning of work is. So you can partition the work based on two criteria, right? One is task parallelism and second is data parallelism. So task parallelism is nothing but parallelizing the different tasks, and data parallelism is like splitting the data among the groups. So let me give an example here so that it can be more clear. Okay. Wait. Okay, let me use this now. Yeah. So let us say that you have this task of same thing, right? Same example, adding +2 or +1 to all the elements inside this. Okay, let us make it slightly more thing. So you have multiple instructions here. Instruction 1 is like adding 2 to all the elements of this vector. Instruction 2 is like multiplying 2. Instruction 3 is something like subtracting 100 or something like that. So these are 3 instructions that you have. And the second thing, the second thing is the data, right? Each element in this contains some data. So what I was trying to say is that there are 2 ways in which you can parallelize this thing. One is instruction level parallelism. So obviously you have the multiple core, right? Let's say you have 3 cores. So what you can do is that you can tell each core to handle a particular instruction. Let's say I1 is handled by this core, I2 is handled by this one, I3 is handled by this one. So this is what is the instruction level, task level parallelism. So here we are dividing the task. So this is task parallelism, and each core independently will perform that instruction on that vector, right? So this is task parallelism. So this is one way in which you can divide your tasks, so you can get parallelism. And the second way is that what you can do is that instead of giving separate instructions or tasks to each core, what you can do is you can divide this vector, right? Sorry. You can divide this vector in such a way that you will give a chunk of data to each core, and each core will perform all these three instructions on all the elements that are assigned to that core. So that is data parallelism. So I hope this was clear. Let me go back to the slides.
Can you please summarize the last part again? Just summarize.
Sorry. Yeah, so I was telling that there are two ways in which you can partition the work, which one is based on the instructions and second is based on the data. So based on data, what you can do is you can divide your data, which in this case is the vector, and on a particular chunk of data in this vector, I mean, particular set of cells in this vector, each code will perform all these three instructions. So I hope I answered your question. Or
Yeah.
there are still.
Sir, when you are dividing the vector into different cores, is every instruction, like all the three instructions, performed by one core on the shared data, like divided data?
Yeah, so all the instructions are performed on this
Set.
chunk of data. So our task, our job here was to perform these three instructions on this vector. So I was trying to divide the, I mean, I was trying to extract some parallelism out of that. So we can either divide the instructions or we can divide the data. That was what I was trying to derive.
Yes.
I hope that was clear.
Yes, sir.
Okay. Okay, let us move back. Okay, so this was about task parallelism and data parallelism. So in general, your program may contain both type of parallelism, right? I mean, your program can have both of it, right? Task parallelism as well as data parallelism. So to understand this, let us do this class in which we want to calculate the sum of n numbers in parallel. So you have this vector in which there are n numbers, and you want to sum all those n numbers and want to output on screen, and that you want to do it in parallel. How will you do that? We just don't want to write the code here, but a high level idea about how we will go or how we will approach this problem. So I request each and every one of you to try this and paste your thoughts in the chat. So I'll wait here for 1 or 2 minutes and then we will discuss how we can do it. So there is some point that I'm going to derive out of this. So let us try this and then we'll discuss.
Also, can you ask folks to mute themselves, like it's causing?
Yeah, please. Unless you have any questions, please mute yourself so that we can have minimal distractions during the session. I'm getting some responses. Splitting data among cores, add individually.
In this example, only one task is there, that is addition. So how do we, like, there are no different tasks?
Yeah, you can come up with whatever splitting or anything, any algorithm that you have in your mind. For now, I just want to get your input so that we can discuss what can be done. So store up the numbers in binary tree and then sum them up. Add n by 2 pairs plus distribute the data numbers and separate each. The results for each core and get final result. Yeah, this one looks good. Task build is man. Yeah, so Devyansh, this will be by n by 2 task what we're trying to be. Like we have just one task here, right? Which is to add the numbers. Okay. Okay, any problem that you're facing, right? Division is okay, but after dividing, let's say, okay, let me just now start presenting my another screen. So any issue that you faced, division is okay. We can divide the work and then each core can perform its own task, but there is something else, right? Some issue that you should face after division. So let me talk about that. So that is what I was trying to highlight in this one. Okay. Yeah, so we can keep this, we can keep algorithm as simple. What we'll do is, let's say you have this vector, right, of 8 elements. And you want to divide it among 4 cores. This way. You have 4 cores, right? So what you can do is you can give 2 elements to each core, right? For performing summation. So that is okay. You can give this to core 1, this to core 2, core 3. So that is what is the data parallelism that we talked about. And this to core 4. But after this, let's say each core performs some addition operation. What it might need to do is that it might need to share the results. So this core 2 might need to share its summation result to core 1. So core 1 will get the summation result of core 2 and it will add it to its own sum. So let's say it was S1 here, then it will do S1 plus S2. Similarly, this thing here, it will send to core 3. So core 3 will do S3 plus S4. So this is fine, but okay, and we can do this for next level also. So core 1 will get S1, S3 plus S4 from C3 and we'll do S1 plus S2 plus S3 plus S4 and this will be our final sum. Right, but there are some issues, right? I mean, not issues, but things that we need to that should strike to our mind when we are trying to solve this problem. First thing is that we need communication between the cores, right? So this core 1 is communicating with core 2 is communicating with core 1. Similarly, core 4 is communicating with core 3. And yeah, so that is one thing. Second thing is, if you see here, core 1 should wait for this S3 plus S4 to arrive. It just can't print the result if it want. Like it just can't go and print the result because it just have S1 plus S2. So it should wait for S3 plus S4 to arrive. And that is what we call it as synchronization, right? So synchronization is also needed. So what I'm trying to highlight here is that just writing, if the cores do not need any sort of coordination between each other, then writing parallel program is easy. But there are this issue of communication, synchronization, and yeah, I think there is one more also. I think I have listed. Yeah, so intercore communication is needed, and this increases the complexity, or this increases the complexity of writing the parallel programs. So some of them are like, as we saw, right? Synchronization, communication, load balancing is also one of it. So let me quickly go back and explain how load balancing will work here. So here this case was very simple, right? We had 8 cells, 8 elements and 4 cores, so we can divide very easily. But let's say your vector is dynamic, so there are new elements that are coming in this vector, right? So it's so your input is dynamic, it is coming during runtime, so its size is not fixed. So this can grow, this vector can grow dynamically. Then in that case, you just can't, you can initially divide the work, right? But later when other element comes in, then you just can't keep on allocating that all the new elements to one single core, right? All these new elements to one single core. Otherwise, your single core will be overloaded, and that is not a good thing because you are not extracting parallelism. This 3 core will be idle, and just one core will be doing a lot of work. So load balancing is also one thing. So I hope this is clear. So these are the challenges that we'll face, and we'll see how to address them as we write the parallel programs. So yeah, any questions?
Communication different from synchronization.
Yeah, I think synchronization is slightly different because synchronization is like each core want to wait for some particular event or something like that, where communication is like so you can include synchronization in the communication itself, but yeah, there is this subtle difference. Like communication is like you want to communicate something, while synchronization is you are waiting or something, like you want all the cores to wait for a particular event. I hope that was clear.
Okay. Sir, can you give an example of communication between cores?
I gave, right, that one in which each core was computing something and then sending the result to the master core.
Yes, but that is kind of synchronization only.
Yeah, but okay, I don't have any different example right now in my mind. Okay, I think I'm lacking the good example here, but yeah, I'll come up with it and we can discuss it in the subsequent lecture. Or in fact, as we'll see, the programs will get more and more taste of how communication and synchronization works.
Okay, thank you, sir.
Okay, any other question? Okay, so basically let us look abroad, or let us look into the overview for this course. So we'll cover this broad 3 things broadly. So we'll cover basic OpenMP programming, in which we'll see scope for the variables, how to perform error checking in OpenMP, and how to use the runtime libraries in OpenMP. So this is scope for the variables in OpenMP. Then we'll see the advanced OpenMP programming, which is about this atomics, reductions, variable scoping, and how to work with loops and so on. So that is the second part. And third is the applications, which is like whatever we have learned in this first and second part will apply it on few of the applications like matrix, addition, multiplication, and convolution. Okay, so that's it. Any questions you have? So that's all from my side. I have covered whatever I wanted to cover.
Sir, I just wanted small suggestions that while attending this course, is there any like we have to prepare before, like a small prerequisite before any programming or any class prerequisites, and any other software which we can use for programming, and any platform where we can practice?
So yeah, you should have this OpenMP compiler. So basically, if you have C++ compilers and compiler, and you can install OpenMP. So I'll share those guidelines in the next lecture. But yeah, basically set up OpenMP on your system. It comes as the extension for the C++ compiler or C compiler. Even Fortran, I think, supports OpenMP. But yeah, we'll see C and C++ OpenMP with C and C++. So yeah, that one thing that you have to set up. And second thing is regarding any prerequisites. I don't think that you need any specific knowledge about OpenMP, but you need some basic programming knowledge with C, C++, that's it, or even other language is also okay, because programming language concepts are quite generic. So yeah.
Any study material which we can like so problems or materials of
So there are some problems that we'll cover during the class, but yeah, if we want, if there is something that we want to delve deeper into, then we can pick the specific. I'll say share the specific problems in the group if it is needed. If something is unclear, then yeah, we can cover that specific scenario, problem related to that specific scenario.
Okay, thank you, sir.